This is Math 432, Applied Combinatorics. I'm Professor Asaf, and today we're going to be talking about matchings in graphs. So matchings happen often in bipartite graphs, whenever you have something that naturally goes together and naturally wants to be paired. For example, if you have a Lego minifig, there's tops and bottoms, and we naturally want to pair a top with a bottom. So we could think about, okay, suppose we had a bunch of minifig tops. So here's some minifig tops, and suppose we had some minifig bottoms. And we can ask ourselves, well, in what ways, how many ways can we pair them, or how could we pair up the bottoms with the tops? But that would be easy, right? We can just sort of line them up and create a map, a bijection. But what we want to do is take into account some constraints. So suppose I say that, okay, it's okay for these guys to, this could go together. I'm going to allow for these sort of vertical. This is one way I could do it. But I want to take into account what if there are other possibilities that I wanted. So what if, actually, I think she would look good with some khaki pants. So we can put her there. And this guy could totally have some gray pants. And the doctor doesn't have to go for the lab coat look. She could end up with some pants like that. And let's see, maybe, just maybe, we'll add in a super long edge so that the purple shirt lady could also have the white pants. Okay, this is an example of a bipartite graph. The edges go from the top level to the bottom level with none in between. It's a two-colorable graph, right? That's equivalent. These could be one color and these another. And all the edges are not monochromatic, so they're going across. So what's a matching? A matching would just be a subset of the edges that I pick that have no common vertex. For example, here is a matching. Taking one edge is always a matching because, okay, there's no common vertex. But here I could do maybe a little bit better. There, that's a two-edge matching. And then maybe I could even go like this, and now I have a three-edge matching. So this is an example of a matching on this particular example of a graph. And there's certain types of matchings that I'm interested in. So a matching is called maximal if adding any additional edge that's not already in the matching, so adding any edge, creates a non-matching. So it's going to have to touch a vertex that's already touched. That's what it means to be maximal. So if we look here and we say, okay, can I add another edge? The easiest thing to do is either go with the top or with the bottom and just say who isn't matched yet. Since there are only 4 things on the top and there are 5 on the bottom, I'm going to go with the top. And I see that the blonde is not matched yet. So where could I match her? Well, she actually only has one thing and it's already taken, so I can't do anything here. So she's out. So no, this is definitely maximal. This is a maximal matching. There is no edge that I can add to what I already have that will stay a matching. And we can see that it's easy to create a maximal matching. Just start throwing edges into your set as long as you don't create a problem. And that'll always give you a maximal matching. It's a little more subtle to get a maximum matching. Slightly nuanced. Maximum if it has the most edges among all possible matchings. So there are finitely many matchings, right? Because there are finitely many subsets. So there has to be a maximum one. Is this maximum? Is this the best we could do? It has 3 edges. Is there a matching that would have more edges? Well, we can see because we have 4 things on top and 5 things on bottom. The most edges we could ever have is 4, right? The most we could do is match everybody up. But in this case, with what I've taken, this is already maximal, but it's not maximum because I can actually visually see that if I take these vertical lines, then I would get 4 edges and everything would work out. But in general, I can find a maximal matching, but it's so hard to see that I've got a maximum. In any one example, I could do it, but I'm looking for a theorem that'll help me know. And the theorem in this particular case that we want to look at is the following. Given a matching, it is maximum. That's what we're looking for. If and only if there is no M alternating path. So what's an M alternating path? That's just going to be a sequence of vertices such that every other edge is in your matching. So these are NM. And the other edges, it alternates. These are not. So the first and the last need to be not in your matching, but all the ones in the middle are in your matching. Let's see if we can figure out how to make an M alternating path out of this. Well, I could add this edge. Let's see, I want to start and end, so let's start here with a blue. I go blue, red, blue, red, blue, red. Let's do it this way. And now there's a blue, but that's not going to kind of work. So let's just count off our vertices. Let's start here. 1 to 2. 2 down to here to 3. Aha. So if I switch up here, I could go 3 to 4. And now I could actually stop there and just take that one piece of it. So here, let's ignore this guy, because these guys are actually pretty well matched, but these guys aren't. So I could take a piece of my matching. It doesn't have to be with the whole thing. So I'm going to ignore this part for now, and I'm just going to look here. There is an M alternating path. It goes blue, red, blue. So what I can do is whenever I have an M alternating path, I can use the path to create a new matching that's going to have more edges. Do you see how? Here I have blue, red, blue, right? So what if I just switched out red for blue? So we'll switch these guys, the same edges, if we can without completely destroying the graph. Got it. And now take the blue away, take your augmenting away. And now look what I've done. I've created a maximum matching. So by iterating this operation of finding an M alternating path, and then swapping out the edges, swap out the blue for red, you can actually prove this theorem. So this is one of the theorems I want you to try to write the details down in the homework. This is an idea for how to do the harder direction of it. Of course, there's another direction. It's an if and only if, so you need to prove two things. You need to prove that if it has an M alternating path, then it's not maximal. And if it doesn't, then it is.